Welcome in. Okay, so the Doppler effect and this particular equation, which we want to be able to know how to use. So first, what is the Doppler effect? Well, the Doppler effect is the following. You have experienced this probably at some point. So if you've ever heard an ambulance or a police car, okay, and maybe they have their siren on, or anything that actually makes noise. Now, if it's standing still, so if you have something which is far away from you, okay, or it can be close to you, but if it's giving off a sound, okay, so we're going to say that that's the source of the actual sound that's given off, and it's going to be at a certain frequency that it's given off. If it's not moving and you're not moving, well, then the wave itself, the wave meaning the sound, is going to be carried through the air, okay, and it's going to get into your eardrums, and you're going to hear a certain pitch, meaning a certain frequency that you have. Now imagine that particular source that gives off, so for example, a police car or an ambulance, starts to move towards you. Now, are you going to sense exactly the same pitch, meaning the same frequency? The answer is actually no, because what's going to happen is that as it's moving towards you, then the sound itself, okay, in terms of the travel, is going to travel at a certain speed. However, the actual movement of the source giving off, okay, the siren, as it's coming towards you, okay, it's going to compress the actual frequencies. So the pitch is going to seem like it's actually higher, right? So you're going to get more cycles per second, okay, which is coming through because it's moving towards you, okay, and it gets closer and closer. Now, if it's moving away from you, so this is, again, so the Doppler effect, so something is moving close to you, or you're moving it close and you're coming in, notice that that means that you're going to be hearing, okay, that particular pitch much faster, so the frequencies are going to increase, okay, as you're coming together. But if you're coming apart, okay, and you're moving away from each other, so even if you're standing still, and let's say the ambulance or a car is moving away from you, then that source, the actual sound that it's carried now, is not going to be compressed, right? It's going to kind of have those rarefactions, okay, as a wave would have. Those particular items, because of the fact that it's moving away, now is going to create this effect that that sound is going to get to you, but the frequency is not going to be as high. It's actually going to be reduced because something is moving away from you. So here's a site which captures this in a very amazing ways. Now, of course, this I didn't code this in, so this is right from the actual internet, okay? And this simulation has been, okay, so written by, so it says here by Andrew Duffy, but it's a pretty cool thing. And it actually shows this concept of the entire process of this Doppler effect. So in here, what they have is the source has a certain frequency. Now they've set it up at 100 hertz, okay? And then initial, okay, the frequency, if nothing is moving at all, right? And you just basically play this out. So this is giving off a sound, right? So that sound is going to be given off. So you can imagine that this is basically like the siren going off. The green line, okay, which you see there, so that's basically you standing there. And that frequency is not going to change. But now, all of a sudden, if you... Now, I'm going to move this further out, away a little bit. Okay, so I'm going to move this shifted away. Okay. So you can see there that that sound, that siren is going off in there. And what's happening is that there's no change in the actual pitch. The frequencies are identical. But as soon as this starts to move towards you, so now let's say this is slowly now moving towards you. Now notice you can actually see the actual frequencies, okay? So they're basically being more compressed. Now you can't see this as much because now, so notice I've set the actual source of the velocity at 0.1 of the speed of sound. So basically it's at 10%, okay, of whatever the speed of sound is. So if the speed of sound is, say, like 330 or 340, it would have been at 34 meters per second, and it's moving towards you. And notice that it adjusts, okay, the actual observed frequency. Notice it's showing us 111 hertz, that it's faster. Now, I'm going to bring this siren right back there. I'm going to reset this thing so it just goes back. And I'm going to make this even faster, all right? So let's say 0.4. Now you can see this much clearer, this Doppler effect. that it's compressing these things, because every time that it actually shoots out a siren, it's also moving at a speed. Now, notice in here, so I'm going to pause this, as it's moving away from you, the actual pitch as it was coming towards you was faster, right? So it had a higher pitch. But as it's moving away from you, notice that the actual sounds, because now it's moving away, so every time it gives off a sound, it also moves at a certain speed. Okay, so it's not as frequent. So the frequency that you will observe is going to be down. And this is what happens. So if any time, you are driving maybe in a car, you have an actual ambulance coming in towards you. So as it comes in towards you, it sounds kind of like the pitch gets higher and higher. But as it passes you and it goes away, the pitch really, comes down, as it keeps moving away. And the further it is away, of course, it's going to get dampened down. So that's what happens. That is the Doppler effect. And we can actually measure this out, through the equation by simply a basic proportion. So here it tells us what the actual results are. So it says that the frequency of this, let's say, siren is at 100 hertz. And notice that if it passes you by, it drops to 71 hertz, which we can see here, that it's not as frequent. Now, if I'm going to, again, kind of reset this back in, and I'm going to pause this out for the moment, notice that the frequency now, because the vehicle is moving towards you, towards the green line, it has jumped to 167. Let's see, how do they get this 167, to be able to see how do they calculate this from this equation. So now I'm going to take a peek here. So it says it's 0.4, meaning 40% of the speed of sound. So let's jump into this right here and try to explain the exact thing. So the source frequency, so this is the source frequency. So this was set at 100 hertz. That is, the actual, let's say, the siren that's going off. This is calculated. Now they said this is rounded probably. So they said 167 hertz. That's what's actually observed when this thing is coming towards you. Now, it doesn't matter what the speed of sound here is, because they've actually told us that the source itself right here is 0.4 of the speed of sound, or simply, 40%. So 0.4 of the speed of sound, so V sound. So that's what this would be. Now, the equation also captures the speed of the observer. Is the observer moving towards or away from the actual source, right? From the siren itself, or from whatever is making the noise. In our case, this was stationary. So this basically was just 0. So what this equation would tell us, so let's see how we get this 167. So this is the speed of sound. This is in the numerator. The observed one is 0. And now this is going to be divided by, this is again the speed of sound. And now, is it going to be a plus or a minus? Now, this you have to, yes, you can memorize it, but you shouldn't necessarily have to memorize it. If something is coming towards you at a certain speed, your pitch is going to increase. So how would that happen? If I actually put this as a positive 0.4, and it was with respect to the sound right there, then I would make the denominator bigger, which would make this entire thing smaller, right? Because it's inversely proportional to it. So that means whatever the source would be, now in our case the source is 100 hertz, so if that was a positive here, then this would actually make it smaller, right? Which means the pitch, was actually less, but the pitch got higher, as something gets closer and closer and it's moving at a certain speed. So this will not be positive, but it will actually be negative in here, so that it decreases. So now notice you're going to get V of the sound divided by, now in this case it's 40% of, so this is going to become 0.6 of V sound. Now again, we didn't need the speed of sounds because this will just cancel each other off, and this would be 100. So what you really have here is you have 1 over 0.6 multiplied by 100, and let's check it out. So what would that give us? So 1 divided by 0.6, and then this is multiplied by 100. And notice that indeed it is 167. It's 167 rounded. in here. Now, that happens, okay, when this is moving towards you. So if this is, okay, moving at a certain speed towards you, then indeed, this will now become right here. So this is going to become negative, just as you saw it here. But what I would want you to think about, instead of memorizing, is it positive or negative, think, okay, is it going to make the pitch higher, meaning frequency higher, or is it going to make the frequency lower? So if it's moving towards you, it should make it higher. So that would mean that it's going to be negative. The denominator should get smaller, so that the fraction overall is going to get bigger. If it's moving away from you, the pitch actually will get reduced. So in that case, it will be positive. Now, if the observer was now moving, so if the observer, if the siren is coming towards you and observer is also coming towards this, notice that's going to, actually compress it even further. So it's going to even increase the sound even more, right? So in that case, if it's going to increase the sound even more, so if the observer is moving towards that, then that would make this positive. But if the observer is moving away from it, right? So if it's moving away, so if the observer is actually going this way, so for instance, imagine that you're driving a car and the siren is coming behind you. So if it's coming behind you, but you're moving, faster than the siren, now most likely the siren will be moving closer if it's the police that's chasing you down. Okay, so in that case, if it's moving faster than this, it's that difference that matters, okay, and that will impact this equation. So this is a really neat thing to see. Now what I would want you to do, so if I'm going to go back in here, I'm going to actually play around. So let's leave the actual source that it's moving at 40, okay, the actual 40% of the sound. And now the observer, I'm going to make the observer move as well. Now let's make the observer, so now let's say that the observer is moving at 0.1. So notice now it's 0.1, so it's positive. So it's moving in this way. Notice that it automatically dropped. Now I'm going to pause this for a moment, okay, within here. So you can see there on the screen because it updates it for you. So the frequency of the observers now is 150. Remember that when it was stationary, it was 167. Now it's 150, and it's moving at 10% of the speed of sound, right? But the source is moving at 40% of the speed of sound. So this is how it works. So if I go back in here and I try to plug this all in, now all of a sudden, so what I need is, because the observer is now moving away from it, so what's going to happen here, this was at 0.1 of the speed of sound, so V sound, that's the observer. And now the question is it going to be positive or is it going to be negative, right? But the observer itself is moving away from the source. So if I put a positive, that would increase that overall fraction. So I actually have to put a negative in here in order to do that. Now, if I do a negative, then what we're going to get is, instead of having 1 over here, so what's going to happen, so instead of this, and this won't be a 1, this is going to be 1 minus 0.1, which is 0.9. So it's going to be 0.9. So this will still cancel, and now you're going to get 0.9 out of here. And now you can see here that this fraction, 0.9 over 0.6, is indeed just 1.5. And 1.5 times 100 is 150 hertz. So that's what you would have, and that's how you can utilize this equation. So always think, okay, is it going to make the actual fraction bigger or is it going to make it smaller overall? So here is one last example on this. This one is actually with numerical values. So let's take a look and see, okay, how we would calculate this. So here's an observer, okay, and the observer is moving at 8.5 meters per second west. So I'm going to kind of draw this out. So what this is, this is what this is saying is the following. So the observer is moving in this direction. So let's make west to the left. So this is 8.5 meters per second. That would have been the observer's speed. So that's this right there. Now, an ambulance is moving at 72 kilometers an hour west. Now, be careful here because the units have to be the same. So they're saying that this is moving at 72 kilometers an hour. Now, what's 72 kilometers an hour into meters per second? So that unit conversion, okay, so I'll leave up to you, okay, but I'll do that very quickly. So we have, this is 72 and then it's going to be divided by 3.6 to bring it back down. All right, so we have this, okay? This will be also west, so this is the actual source, V of the source, and that is equivalent to 20 meters per second. All right, so overall, so that's what I have. So that means that the source is moving, but the actual observer is moving away from it. Okay, so that's what happens. Now, what frequency does the observer perceive? So this is now kind of a two idea question. Well, first of all, okay, if this is behind, okay, and it's chasing it down, it's going to perceive a certain frequency. But if it's now passes the observer and moves away, the frequency is going to change. So let's do both, okay, so that we can see this. So the observed, so I'm going to put F0, okay, for the observed right here is equal to. So let's do the first case when the source is behind and it's coming towards this. So now whatever the speed of sound is, they tell us is 335 meters per second. 335 meters per second. The observer, this is 8.5. All right, so that's what happens there. Now notice it's moving away from the source. So in this case, it would make, okay, the frequency, okay, the pitch go down. So this is going to be negative in this case. The denominator is 335, and now this is going to be 20. Now this again, so notice it's moving towards the observer at a certain speed. So this is going to be also negative. Okay, so both of these are going to be negative in here. And now the source itself is 125 hertz. Okay, so that's what the siren is going off at. So that would have been the first one. Now, while the second one, so FK0, put 2 over here. So what's going to happen is, let me rewrite all of these right here. This is 335, 8.5, okay, and 20. So now if it passes it by, right? So if it passes by the actual observer. So now what would happen is, you know, this would have been in the front, okay? And let's say it passed it by, and this is now chasing it, okay, from behind over here. So now it's moving away from the observer. So in that case, now this is going to be a positive right there. Now the upper one is still going to be negative. So this, okay, so right here, so as it's going through the numerator, okay, so because it's trying to chase it down. Now if it's trying to chase it down, so if you would freeze the source itself and it's trying to chase it down, okay, then it would actually increase the frequency, the pitch, right? So this right here, okay, it would have been positive. And sorry, I think I said negative, so this is positive now in this case, and this would have been 125. So now we can substitute both of these back in here, and we can get exactly what the frequencies are in both cases. So let me do that in fast forward fashion. So I'll do the numbers, and then I'll come back. All right, so there you have it. Okay, so I rounded it to 2 significant figures in here. So that's what it would have been. So the higher pitch and then the lower pitch, that's what you would have noticed. All right, thanks for watching. We'll see you in a future video. Bye, everybody.